So I'm going to present you the SURFSHAPE project, which was accepted in the last round of the call for proposal in the LabEx Manutech size in the EUR. This presentation is going to focus on presenting you the framework of the project and what we would like to do with it. So we will start the project in October, November this year. And now we are already kind of starting to work on it and basically define the different steps on what we want to do with it. So the project is about surface shaping. And so the shaping has two meanings in there. We both want to shape the pulses. So I'm going to explain to you in the first part what I mean by this. And then we want to use those non-trivial pulses to, in return, shape the surfaces. So do some like surface processing with these shape pulses. And when we talk about shaping the pulses, basically we want to shape them on all their parameters. So I'm going to come back to this in a minute, but I mean temporally and spatially. This project will hire a postdoc that will start by the end of the year. And it's linking the Laboratoire Hubert Curien with myself and Ciro D'Amico, Jean-Philippe Colombier, Florence Gallarelli, Razvan Stoyan, and also the people in the LME in Lyon, which will have more like a chemistry side to the project, which will be basically more towards the end, towards the application of what we want to do with this kind of surfaces we're going to make with the shape pulses. And another side is we would like to include Nicolas Compère of the Manutech USD, which presented a bit earlier, because the shape pulses, so I'm going to present you the shape pulses now. And I'm going to present you in the last three parts that you see at the bottom, a specific applications that interest myself specifically. But the goal is also to make a platform with those shape pulses that once we have the technology, everybody can use it and we can think of different applications and open it to broader collaborations. Okay. So this is another layout of the project. So typically we want to shape pulses. So I'm talking about femtosecond ultra-fast pulses, typically 800 nanometer central wavelengths. And what you have usually out of the box is a Gaussian pulse, both in times, which means the time envelope is a Gaussian, and in spatial profile, which means the intensity distribution along the transverse propagation is also a Gaussian. And what you can do is make some non-trivial spatial shaping, which means you start modifying the structure of the pulse amplitude in space. And you can also do some temporal shaping, which means doing some non-trivial variation of the time envelope of the pulse. When you do that, what you can expect is to basically have some smart pulses in a way that will allow you to do some nanostructuration that you couldn't do with the basic Gaussian pulse. So what has been shown, for example, in other work by other groups before, is that if you have pulses, for example, with a rotating phase, like I show here on the left, you can start designing structures that themselves has some kind of twist, okay? This twist, more scientifically, we will call that chirality. And I would like to use them to interact with chiral matter, typically chiral molecules. And I will come to some application of this in the second part of the talk. Okay, so first I'm going to talk about designing the shape pulses. So typically when you want to do pulse shaping, you have an element, an optical element that is a pulse shaper that allows you to transform the pulse. And a laser pulse is defined by three typical parameters. So you have its dependence in the amplitude in real space, how the amplitude is distributed. You have its time dependence, and you have a third one that I didn't talk about yet, which is the polarization state of the pulse that I write as epsilon. So it can be linear, it can be circular, but it can also be non-trivial, which means it can be something that will vary in time between pulses and between within a pulse. And there is something that is quite common in pulse shaping, but also in optics, is that when you want to act on a pulse, you realize that, of course, the interaction, you think about it more, the most intuitively is in real space and real time, But if you want to transform it, it's simpler to do it in the Fourier space. So both the Fourier space of the 3D space we live in, but also the Fourier space of the time. So typically, what does it mean? Okay, what does it? Okay, I'm gonna present this first for you. What you do is that, for example, for the time domain, you come with your pulse and you use a grading, so you can spread it in the Fourier space, which is basically the omega axis, right, corresponding to the time. And then for each of the Fourier components of your pulse, you will act on them with this kind of screen, which is basically as many pixels that you can address. And you basically change the phase retardation of each of the Fourier components. And then you can recombine, and then out of this, you get your shape pulse. So it's a lot of Fourier optics. So how can you use this for? One of the simple application is to directly use those non-trivial pulses. And for example, this is something I worked on in my PhD, so some time ago. When basically, for example, when you do nonlinear optics, typically you have many processes coming onto the matter. And if you want to do some spectroscopy out of this, so you want to get, you have many pulses coming and many processes are happening. And because of the momentum conservation, the signal you want to look at will be emitted in some direction. Okay, but this can be very complicated because you basically need to align on your optical table pulses coming in all kinds of directions. So what you can do with pulse shaping instead is to go to a collinear geometry. And for example, here's the pulse 1 and 2, you make them collinear. So the setup is a lot simpler, but what happens is that a lot of processes will overlap with each other. So this is where the pulse shaper come into play. What you do is that out of one pulse with a pulse shaper, so playing in time domain, you can make two different pulses with a delay you can control, and more importantly, a phase difference between the pulses you can control. And if you repeat the same experiment with different phase combination, and then you take basically sum and differences of the different signal you observe, you can extract the one specific process you want to look at. So this is called phase cycling in nonlinear spectroscopy. And basically it's a way to circumvent phase matching for the people who are into nonlinear optics. Okay. And another thing you can use pulse shaping for, which has been used a lot, is for controlling. So this was also intended to connect a bit with the rest of the week on the people in the week that are more into like the optimization and like data processing. What you can do is that you can use these pulses on the sample, and you can look at a given observable. So it could be an optical observable, typically like a fluorescence or something like this, or it could be a yield, for example. I'm going to come to that just in the next slide. And from this observable, basically you try to optimize it. So basically you loop, you have an algorithm because your pulse shaper is controlled by your computer, and basically you address each of the phase retardation in order to maximize some given observable. So when you do that, you do what is called optimal control, also called as quantum control. So for example, okay, things are a bit out of order, but it's not too important. So for example, an application of this is the following. This is a very important paper that was done in the late 90s, which kind of trigger a bit this quantum control process. What you want to do, for example, is control the photo dissociation product in an experiment. So what people did back then, they got like some organometallic complex, and they do some photo dissociation with a shape pulse. And what you can do is that depending on the shaping strategy, so for example, two shaping strategy correspond on the left bar, or the second one correspond on the right bar, you can maximize the yield of one given component. But when you do that, of course, you treat your shaping system as a black box that you optimize until you get what you want to see. Okay, I'll skip the rest because time is flying. For the pulse shaping strategy, to make it a bit more concrete, this is what we are currently building in the lab. We have this spatial light modulator, which is basically this screen with all the pixels here you can address. And we are building this setup, which you have gratings, you spread your beams, and you go here through the active element of the spatial light modulator. And out of this, you can get your temporal shaping. an extra degree that we want to control here. As you can see, we have two screens because by playing basically with a set of polarizers and playing with the polarization of the incoming beam, we can shape almost independently the two polarization components of the pulse. So which means we have control both over the time and the epsilon polarization in the first slides I was showing you before. And this can be combined later on with spatial shaping strategy. So by spatial shaping, we can use some 2D shaper. So now you come with a collimated beam. So what does it mean? It means you have the different K components of your incoming beam. And each of them now in space will have a different phase retardation. So you have the same principle, but now you work in the K on real space. But if you want to go for something simpler, and you don't need to address by computer complex shape, and you don't need to have a feedback loop on the spatial shaping, you can also have simply optical components. And one thing that interests me in particular, that I will address in the second part of the talk, is to induce some vorticity in the incoming pulse. So the idea is to have this kind of optical components, which are like Fresnel zone plates, but you can also have a spiral phase plates that induce a spiraling phase rotation. So it means your pulse is having an angular momentum. One last feature of shaping I want to discuss. So this is like following a bunch of recent results I did this year. Is that you can also have you can connect with a theory also with your shaping. Because so here, for example, just to highlight this, I present you a molecular dynamics. So this is a cis-trans isomerization of azobenzene. So you have a pulse that photo excites the azobenzene, and when you go from the cis geometry to the trans geometry. If you want to have a quantum perspective on this, what happens is that basically you take the ground state wave packet and up you bring it to the first excited state. And then the wave packet can freely evolve in the excited state until it reaches a place where the two potential energy surface can connect and it can relax. But instead of relaxing back to the cis geometry, it can be sent to the trans geometry. So this is what's happening. And what you would like to follow experimentally, typically to follow the structure, is to use diffraction experiments. So here I show you some simulated X-ray diffraction. And typically, in X-ray diffraction, when you think of it, usually is that you are probing the Fourier transform of the ground state and the excited state charge density, which is all good. But when you do this, you don't really have an easy access to what is happening here when you create a coherence between the two potential energy surface. So after some, what we highlighted after some analytical work, we saw that some extract terms actually appear in the signal, which is those two last terms here, but they are much weaker. So they are much weaker than what you see. So you don't see them right away from the diffraction spectra, but they are there, and they are a signature of only the crossing for the coherence here, which means that you basically have a signal that appear and disappear just at the quick time when the wave packet crosses through the conical intersection. And by sending the wave packet propagation and combining with a pulse shaping strategy, so basically we have an optimization of the pulse envelope within the dynamics. The dynamics, the quantum propagation program gave us that it finds you need to hide an extra IR pulse. So this here is a result of the quantum propagation, and it automatically finds on top of the photo-exciting pulse an extra IR pulse that is centered at the time when the wave packet will cross the two surfaces, and with an energy that corresponds more or less to an average, so over the wave packet distribution of the energy difference between the two surfaces. Okay, so now, after talking to you about the shaping, I'm going to present you what I want to do with these shape pulses. And one of the things that interests me is to generate chiral light. So I'm going to go very fast on the chirality, but basically chirality means objects don't have inversion symmetry. The typical object is your hand. So your left hand on your right hand, they cannot be superimposed. They actually have a mirror symmetry between the two. And this is very important, especially for the biochemist, because a lot of the molecules linked to biology have a specific chirality. Typically, all the amino acids are left-handed, and all the sugars important for biochemistry are right-handed. And for a long time now, this is known for a long time, a way to address that, to discriminate between the two enantiomers, is to use circular polarization, which corresponds to chiral light on the polarization degree of freedom. But very recently, people have been starting to look at chiral light with spatial degree of freedom, and this can be associated to spin and orbital angular momentum of the light. A way to look at this, for example, so this is well known for people who do electromagnetism, is that usually you have a conservation equation that I show here, which basically tell you that the rate of change of the intensity of your pulse is linked to the flux of the Poynting vector. So basically, you don't create the energy. What is changing in your local area is what is coming in or what is leaving. And so this is a very old paper here. You see from the 60s. So okay, one step backward. This is known for pretty much since Maxwell. So it's like 150 years old. And now you have a more recent result, but still quite old. In the 60s, Lipkin came up with new conservation laws that find new conservation equation, which I show you here. Okay, and when you look at this, you realize that this is a pseudo-scalar. So it means it has the right property to be a chiral quantity of light. Okay, and this was kind of left away for like 50 more years. And then in the 2010s, the group of Adam Cohen basically shows that this chirality of light, if you maximize it, you are creating superchiral fields, and then you can use it to enhance all those chiral signals that in return can help you to probe the chiral molecules, which give you otherwise quite weak signals. So this is one of the goals of the pulse shaping I want to pursue. I would like to use the pulse shaping to maximize this key term. This I will skip due to lack of time. And okay, so I told you we can generate this superchiral light using either the spatial or the temporal pulse shaping. And now this is where we connect to the surface nanostructuration. There have been a bunch of recent works from this group of Subayev and also the group of Nivas, which basically show you that if you come with vortex beams, so here I'm talking about the spatial distribution, you can generate such structure. So this is like single pulse, nanosecond, 500 nanometer visible pulses. And you can also use the polarization degree of freedom to generate such structures too. And depending on the polarization states, basically you can have this kind of ripples that we have a chiral structure. Okay. Just to go fast towards the end, why do we want to make chiral surfaces? I mentioned to you like chiral signals that can be used to probe chiral molecules. So typically you have like circular dichroism that is being used quite a lot and is quite useful, although it is a weak signal. It's usually done in the UV or in the visible. So it's probing electronic transitions. And there is another signal that has been developed in the 70s, 80s, which is equally rather weak, which is a Raman optical activity. So it's typically a Raman signal. So you come with photon, you scatter them, and you look at the Raman yield. But now you can do this Raman signal, and you can look at the difference between the yield between left and right polarization, just like you would like to do for circular dichroism. So what is interesting there is that you probe directly vibrational transition, which have more structural information than the electronic ones. And the selection rules are different. This is well known between, for example, the complementarity between Raman and IR absorption. But I told you the signals are quite weak. This is example of the signal, what you can get, but I skip on this. So those signals are quite weak. And now what has been done too is in the community of the surface enhanced Raman signals is to use a shaped surface, typically with nanostructures on the surface, and to use this to enhance the Raman signal. So there have been enhancement factor of like thousands or tens of thousands. The theory finds even more with like millions of thousands. And when you have these nanostructures, typically what you create is that you create some hotspots of intensity, like with the plasmon resonance, you have some hotspot of intensity, and then the molecules that are at the proximity, they feel a much higher field intensity. So then the Raman signals you can detect is enhanced. This is, for example, typically structures that I did now 10 years ago. And that can be used for making what is called a SERS substrate. So typically you do your Raman experiment with and without the SERS substrate, and you observe a strong enhancement. So the goal will be basically with this kind of chiral surfaces to bring this SERS mindset to the Raman optical activity, so to make so-called surface enhanced Raman optical activity. So this, of course, is a long-term goal, and this is where the collaborators with the LME will come in when we want to absorb chiral molecules on the surface near those chiral structures. But now there is many open challenges, and I will close the talk on this. What are the most important parameters for the surface structurations, right? Because if you have femtosecond pulses, and actually, if your surface structuration is mostly due to some hydrodynamic dynamics linked to the deposition of heat, can you actually feel this non-trivial shaping in time or in space of your pulses? So this, we have a lot of ongoing discussion with Jean-Philippe, for example, and it's highly non-trivial. Same thing, how does light chirality engage with matter, right? So I presented to you this key term, which is a local field chiral density, but it would be, there is some insight in the literature that this is an important term to engage with molecular chirality, but at the same time, there is also people who started to work on the theoretical side of the surface enhanced Raman optical activity, and some people say it's only field gradients that are important. So in that case, do you actually need a strongly chiral field to probe chiral molecules? This is still open to debate. And now, if you want to make chiral surfaces with a closed loop system, what I was mentioning before, like with this kind of feedback loop to optimize your pulse until you create the surface you want, you need a way to in situ probe the structure you're making, right? So we need to find the right observable, which can be, which will typically be an optical measurement, could be fluorescence, could be some scattering, but we need to see which one can really assess if we are creating chiral structures or not. So far, I was talking a lot about like the spatial and the temporal shaping kind of in a disjoint manner, but of course, in the end, it would be nice to think if we can combine everything. I will end there. I remind you that, of course, the pulse shaping, which was the first part of the talk, once it's there, it can be used for many things. So I hope we can trigger a lot of interesting discussion on how to use them for all kind of other application. And now you also know my personal interest into light chirality and probing chiral molecules with it. Thank you for your attention.